Hi guys, welcome to this new Python tutorial. In this tutorial we will be discussing the use of dynamic programming. We will explain what it is and we will actually see how it works using a very popular sequence known as the Fibonacci sequence. So dynamic programming is actually a set of techniques, mainly these three, known as recursion, memoization, and bottom-up, and this is often also called tabulation. So I'll now discuss these techniques one by one and give you an example how you could apply them to solve a problem. So let's discuss the concept recursion first. What is recursion? Well, recursion is essentially a concept from mathematics that we can apply to a function. So a function is basically something which takes inputs and it gives us an output. So it's like a box. It takes an input and it returns an output. And so basically what recursion is that the function calls itself. So it is basically defined with itself. So this sounds kind of unclear. But we will see with the example, and I hope it will become more clear. What is very important is that a function which is recursive usually has two parts, and only one part, or it has more parts, but basically one part is recursive and the other one is not. And you might be wondering, well, if the function calls itself and it continues to do this, then we will get an infinite loop. So basically it would continuously call itself and would just keep spinning around forever. And that's the reason why these two parts are very important. So eventually it will stop calling itself because a certain condition has been met. So let's actually see how this would look in an example. So the example I want to discuss is the example of a Fibonacci sequence. If you're unfamiliar with that, Fibonacci is basically a sequence of numbers which is defined as the sum of the previous two numbers. So if you add 0 and 1 together, then you get 1. If you add 1 and 2 together, you get 3. If you add 3 and 5, you get 8, 8 and 13, and this continues. And so basically this series or this sequence of numbers can be generated using a recursive function, and I'm going to discuss that now. So we're going to define a function, we're going to call it fib of n, and the function is going to have two parts, right? So this is the first part, and this is the second part. And if you look like where's the recursion happening? Well, here, right? Because you see that the function fib is being called again here, twice a second, exactly. So let's discuss this first part. What is it doing? So if the number n is less than or equal to 1, then we return n. So basically it is taking these two cases. If the number n is equal to 0, then it's less than 1, we will return 0. If it's 1, then we will return 1. If it's 1 here, then again, this case also will return 1. And then for the number 2, we have to go to the else statement. And then what is it going to do? Well, it's going to use the definition of the Fibonacci sequence, and it's going to say, well, it is just the sum of the previous two elements. So for 2, it's going to say, well, we need to take this element and this one and add them together, and then we get 2. And you could basically put in any number you want. So for example, you could want the 0, 1, 2, 3, 4, 5. If you want the fifth number, then you will just put in 5 and it will compute the Fibonacci number within the Fibonacci series which matches that number. So let's actually look at this in a different way. If you're actually looking at the previous implementations of the previous function, we are recomputing the function values every single time. And we are doing that multiple times. So a method that is also part of dynamic programming is called memoization. And so what that would basically mean globally is we would have to store the solutions to our subproblems in an array or a list. And what this basically means we can do is we can, instead of recomputing, just take these values out of the list, and that will be faster, of course. But you know, a negative consequence is that we have to keep track of this list of numbers or values, and that requires space. So let's see what I mean more visually. So this is just the function which I previously defined, and this is basically a graph of the function calls. So in this example, we're going to compute the Fibonacci of 3, and what will happen is we will actually have to calculate the Fibonacci of 2 and 1, right, which you can see in this line. And then for 2, we have to find 1 and 0. And if you're looking at this graph, right, you can see we are actually computing this value for fib of 1 twice, right? But we wouldn't actually have to do this if we were to store this value. And so this is kind of a trivial example, right? Because this is a very small number, but if we go and increase to higher numbers, this can become actually problematic because we're going to continuously recompute this value every single time, which is very inefficient. So I'll right now show you a memoized implementation of Fibonacci. And so the way I've chosen to do this is using a dictionary. So this would be a dictionary called Fibs, and in this dictionary we're going to store all of the basically numbers we have already computed. So as you can see, 0, 0 is in here and 1, 1. This is just to start out. And then the new function would basically check each time we're going to compute it if it's not in the array, right? So we're going to check if it's not in the array, well then we have to compute it, right? Using the definition we previously used. But if it is in the array, well, then we can just return it because it's already there. So we don't have to compute anything. And so what would be the improvement we actually realize by using this memoization? And it's actually pretty significant. So if you look at the previous function, right, let's just go back. What would be the time complexity of this function? Well, we are going to make at most basically n function calls, and every single time we make 2 calls, right? So the time complexity would be O of 2 to the n. So it would basically, it would be exponential. So this is very bad. If we now look at this implementation, well, how many calls are we going to make? So a way we could look at this is we could say that the time complexity for n is equal to the time complexity of n minus 1 plus time complexity of n minus 2, right? But this one is stored in the array, so it's constant. So this would be t of n minus 1 plus 1. And this continues, right? Because every time we store a previous subproblem, we have a constant time by retrieving it because it's a dictionary. So in the end, we will just have O of n, linear time, because we're going to do at most n computations, and then we're going to store it inside of this dictionary. So there's also a third method, which is known as the Bottomup method or the tabulation method, which basically kind of reverses the problem. Instead of starting at the top, we start at the bottom. We start with the subproblems, and this has a number of advantages. And the first advantage is that we do not have any recursive calls. So if you have actually used recursion in several programs before, you might know that if you have a lot of recursive calls, then the program will time out. It will basically exceed the limit of recursive calls that you can make. And what is also possible using tabulation is that sometimes you will not have to store all of the previous subproblems we already computed. And so to visually look at this, with a bottom-up method, we basically start here. And we then say, all right, let's compute the value of fib of 1 and fib of 0. And then let's use this to compute fib of 2. But we already have fib of 1, so we don't have to recompute this. We just use the previous value, fib of 1. And then we use fib of 2 and 1 to compute 3 again. And we can basically apply this structure for all of the Fibonacci numbers we wish to compute. And so if we look at a bottom-up implementation, well, the first thing which you might notice is that we do not need a dictionary right now, right? The only thing we actually need is we need to store 2 values, the previous Fibonacci number and the current Fibonacci number. So again, we check if the n is 0, then we return basically 0. So this is the first case in the Fibonacci sequence. else, well, then we're going to compute it, and we're going to only keep track of the previous two basically nodes in the computation graph. We only are going to remember these two guys, because the others, we have already computed that and stored their values in here. And what we're going to do is we're going to iterate over n-1, so basically everything excluding the first number. And then we're going to say the new fib is going to be the definition of Fibonacci here, the previous number plus the current number. And then here we are just going to update our previous number and our current number, and we're going to do this n-1 times. And this is basically just in programming what I just explained in the graph. We just move up to the top. And if you want to see the time complexity of this method, well, this here is a constant time operation. These two guys are also constant time. And the only thing in here is we actually have this for loop of n-1 times, executing 3 constant time operations, no recursion. So the time complexity of this method would just be linear, would be O of n. And the space complexity is also better than the previous memoized version because we do not have to store any values inside of basically a dictionary. So this was my presentation on basically the use of dynamic programming, and I explained this using a example, the Fibonacci sequence. I hope you enjoyed the video. If you like watching these videos and programming problems, consider watching the other videos in this series, known as Problem Solving with Python. Please subscribe if you like the content, leave a like, and thanks for watching.